So let's talk about a really audacious idea. There's a theory out there making a wild claim that four of the biggest, most stubborn puzzles in all of physics, they're not actually separate problems. They're just different symptoms of one single event from the dawn of time. I mean, really let that sink in for a second. We pour billions into all these different experiments, right? We're hunting for dark matter over here, trying to figure out the whole matter-antimatter thing over there, explaining dark energy, solving the black hole information paradox. What if the key to all of them was hiding in the exact same place? Well, that's the core idea behind a framework called unified dynamics. All right, let's get into it. Before we can even touch the solution this theory proposes, we gotta quickly go over the problems themselves. And trust me, these are the big ones, the kind of stuff that literally keeps physicists and cosmologists up at night. So first up, we've got the missing mass, right? Dark matter. Galaxies are spinning way too fast. They should just fly apart, but they don't. Something invisible, making up a whopping 85% of all the mass in the universe, is holding everything together. Then there's the matter imbalance. The Big Bang should have made equal amounts of matter and antimatter. They would have just, poof, annihilated each other, leaving nothing but light. So why are we here? Why is there stuff? Next, the energy of nothing. Yeah, empty space isn't actually empty. It has this tiny bit of energy, what we call vacuum energy, and it's making the universe expand faster and faster. The question is, why is this value so incredibly small but not zero? And finally, the big one from Stephen Hawking, the information paradox. When something falls into a black hole, is all its information just deleted from the universe forever? Because if it is, that breaks some of the most fundamental rules of quantum mechanics. Okay, four gigantic and on the surface totally unrelated problems, but unified dynamics says no. There's a master key, and that key is a single event, a cosmic phase transition that happened in the fiery, chaotic moments of the very early universe. And here's the name for it right from the source material. The Z2 framing phase transition on the tetrahedral IFS lattice. Okay, I know that sounds super technical and complicated, but the core idea of phase transition is actually something you can totally wrap your head around. It's surprisingly intuitive. Let me show you. Just think about a chunk of iron. When it's super hot, all its tiny magnetic bits are pointing every which way. It's a total mess, completely disordered. But as it cools down, past a certain point, bam, they all suddenly snap into alignment, and you get a strong, uniform magnetic field. Well, this theory suggests that the very fabric of the universe did something just like that. There's this fundamental property they call the framing field. You can kind of picture it as a hidden directional grid for spacetime. And it went from a hot, chaotic, random state to a cold, organized one. And it's the fallout from that snap that we're so interested in. And what's really key here is that this wasn't just some instantaneous flash. It was a two-stage event. First, when the universe was just unbelievably hot and dense, we're talking around 100 giga-electron volts, the stage was set for creating that matter-antimatter imbalance. Then, as the universe cooled way, way down to about 249 kilo-electron volts, the framing field itself froze into place. And that freeze-out is supposedly what created dark matter and the energy of empty space. This two-step process is absolutely crucial. All right, so we've got our key, this two-stage phase transition, and we know when it happened. Now for the fun part. Let's see how this one single event claims to unlock all four of those massive cosmic mysteries. First up, let's tackle the big one. That missing 85% of the universe's mass, dark matter. Where in the world did it come from? So the theory goes like this. As the universe snapped into its new ordered state, little bits of the old chaotic phase got trapped. Think of them like leftover artifacts. These aren't just single particles, though. They're stable composite structures called neutral packet relics. And the key thing is, inside these packets, the fundamental framing charge cancels itself out perfectly, summing to zero. And since they're neutral in this way, they don't interact with light, they don't interact with normal matter, which, is the perfect recipe for something we'd call dark. And here's where it gets really interesting. This isn't just some hand-wavy story. The theory makes a concrete, testable prediction. Unified dynamics calculates the mass of these dark matter relics to be right around 2 mega-electron volts. Now that number is super important because it places this candidate smack dab in the light-dark matter window that a bunch of new experiments are specifically designed to look for. And that means the idea is falsifiable. Scientists can actually go out and test this. If they look in that energy range and find nothing, well, that's a huge problem for the theory. But if they find something, wow, that's a massive win. Okay, that's mystery number 1. 3 to go. Next up, our very existence. Why is there any matter in the universe at all? So, back in the day, a physicist named Sakharov figured out that you need 3 specific conditions to be met to end up with more matter than antimatter. It's like a cosmic recipe. And guess what? This theory claims its phase transition serves up all 3 ingredients on a silver platter. The first condition, baryon number violation, that happened through physics we already know about back in that hot early stage. The third condition, a departure from equilibrium, the sheer violence and speed of the phase transition takes care of that. But the really amazing part is the second condition, CP violation. The theory says the very dynamics of the transition are lopsided, with a very specific predicted asymmetry phase of exactly 60 degrees. To put it simply, during that critical moment, the laws of physics were playing favorites. They weren't quite even-handed with matter and antimatter, and that tiny, tiny bias, repeated over countless interactions, was all it took to tip the scales and leave us with a universe full of matter. All right, next puzzle on the list is the cosmological constant. Or, why does empty space have this weirdly small, but definitely not zero, amount of energy? Let's go back to that freezing iron analogy. When you freeze a liquid to make a crystal, it's never perfect, right? You always get tiny little flaws, dislocations trapped in the structure. Well, the theory says the exact same thing happened to the universe. As that fundamental framing field snapped into its ordered state, it trapped little imperfections, defects in the fabric of space-time, and those defects contribute a tiny bit of residual energy to the vacuum. That's why the energy isn't zero. Okay, but that's only half the story. The real puzzle is why it's so mind-bogglingly small. Our best quantum theories predict a vacuum energy that's 120 orders of magnitude bigger than what we actually measure. That's a 1 with 120 zeros after it. It's famously called the worst prediction in the history of physics. So what gives? Unified dynamics says there's a built-in mechanism, something called Banach screening, which comes from the weird fractal-like geometry of its fundamental structure. Now, you don't get to get the math, but the core idea is incredible. This structure just naturally cancels out almost all of that ridiculously huge energy, knocking it down by 120 orders of magnitude to match what we see. And that brings us to our final cosmic mystery, Stephen Hawking's legendary information paradox. Does a black hole really act like the ultimate shredder, destroying information forever? The answer this theory gives is, well, it's beautiful in its simplicity. It says the paradox isn't a paradox at all. It just never happens. See, in this framework, information is encoded in a fundamental carrier that is strictly, absolutely conserved in every single process in the universe. Information literally can't be destroyed, any more than energy can be created or destroyed. So when a black hole forms, that information is just redistributed. It eventually leaks back out, subtly encoded in the quantum entanglement between particles inside and outside the event horizon. Okay, let's just step back for a second and take this all in. We've just walked through how a single event could potentially solve 4 completely different massive problems. That's already pretty amazing. But the real test of a powerful unifying theory isn't just explaining old puzzles. It's about making brand new predictions about other unrelated things that we can actually go out and measure. And folks, this is where it gets really, really compelling. The theory makes these predictions with 0 fudge factors. There are no dials the theorists can turn to make the numbers match up. These values pop right out of the core mathematics. For instance, the spectral index, which is basically a measure of how lumpy the early universe was, is predicted with stunning accuracy. The mass ratio between 2 fundamental particles, the tau and the muon, the prediction is off by less than 0.1%. And its prediction for how much of the universe is dark matter? It's right in the correct ballpark. Again, these aren't just tweaked to fit the data, they are direct outputs of the theory's central engine. Ultimately, what we're talking about here is a completely radical shift in how we think about the universe. For the last century, the holy grail of physics has been to unify geometry, that's Einstein's gravity, with matter, which is the standard model of particle physics. But this framework, unified dynamics, says we've been looking at it all wrong. It's not about unifying 2 separate things. It says that matter and geometry are just 2 different projections, like 2 shadows cast by one deeper, more fundamental reality. They're just different expressions of one underlying substrate grammar. And that leaves us with this one final, really provocative thought. The fundamental building block in this whole theory is a simple shape, the tetrahedron. Everything we see, all the mind-bending complexity of our universe, dark matter, the masses of particles, the very fabric of space-time, is proposed to just emerge from the simple rules of how this one shape can connect to itself over and over again. Could the entire cosmos really emerge from the rules of a single shape? It's a bold, maybe even crazy idea.
but it's an idea that's trying to answer some of the deepest questions we could possibly ask.